So we are going to estimate the area under the graph of y equal 1/2 root x from x equals 0 to x equal 4. So the way we're going to do that is we're going to use 4 approximating rectangles, and we're going to be using right endpoints. So the first thing I'm going to do is I'm going to graph this function. And I'm going to start by making a table of values and plotting some points. But you should be familiar, this is just a transformation of the square root function. So in this case, if x is equal to 0, then I'm going to be calculating 1/2 of root 0, which is just equal to 0. If x is equal to 1, we have 1/2 root 1, which is just 1/2. So let me just plot those 2 points. Continuing, if x is equal to 2, we have 1/2 root 2, and that is approximately 0.707. So about 0.7. Okay, and if x is equal to 3, we have 1/2 root 3, which is about 0.866. And if x is equal to 4, I have 1/2 root 4, which is equal to 1. So the graph of my function looks something like this. Okay. So how am I going to use 4 approximating rectangles? How do I use 4 rectangles to estimate this area? So this is the area that I would like to estimate, the area enclosed in here. How do I estimate that area using rectangles? Well, what we're going to do, if we're using right endpoints, what I'm going to do is I'm going to create 4 rectangles. The bases of the rectangles are going to lie along the x-axis. So these are the bases. The heights are going to be given if I use right endpoints. I'm going to look at the base, I'm going to take the right endpoint, and I'm going to plug it into the function to give me the height of the rectangle. So that would be my first rectangle. So let's just go through that process. So in this case, the base of my first rectangle is from 0 to 1. The height, if I use the right endpoint, is given by f of 1. Okay, and so the first rectangle looks like this guy. The second rectangle base goes from 1 to 2. Since the right endpoint is 2, the height is given by f of 2, which is just the point on the curve. So this is my second rectangle. The third rectangle has base from 2 to 3. The height is given by f of 3, and so this is my third rectangle, and so on. Here's the fourth rectangle. And so I'm going to add up the areas of the 4 rectangles to give me an estimate for the area under the curve and above the x-axis. So let's go through that process. So the actual area is approximately R4. I'm going to use this notation to denote that I used 4 rectangles and I used right endpoints. And this is equal to, so let's look at the first rectangle. What is the area of this rectangle? Well, it's the length of the base, which is 1, times the height of the rectangle, and that is given by f of 1. So let me just write that down in this form. And I'm going to add the area of the second rectangle, that's this guy. The base is also 1. The height of this rectangle is given by f of 2. Now the third rectangle, again, base 1, height f of 3, plus the area of the fourth rectangle, base 1, height f of 4. Now using the table I created here, I can fill in those values. If I want, I can use these values. If I use these values and plug them into my calculator, though, I can get a better approximation since I won't be rounding. So let me just do that. I have 1 times 1/2 plus 1 times 1/2 root 2 plus 1 times 1/2 root 3 plus 1 times 1. And if I plug that into my calculator, I get approximately 3.07. Suppose that this function f of x represented the velocity. So this was like velocity at time x. And let's suppose x was time in seconds. And let's suppose, so let me just write that down. X is time in seconds. And let's suppose that f of t, we could even just rename it a v of x and say, let's suppose that f of x is v of x, which is represent the velocity in meters per second. Okay, so let's suppose we had this situation. So one question you might ask is, can I, if I know the velocity at these particular time intervals, so for instance, I know that we started with a velocity of 0, and then when at time 1 the velocity was 1/2, time 2 the velocity was 1/2 root 2, etc. Can you give me an estimate of the distance the particle or the object traveled? In this case, you could, right? So let's suppose on that first, so from time x equals 0 to time x equal 1, over that 1 second time interval, can I estimate how far the distance that my object traveled? Well, if I know that it was traveling at 1/2 meter per second at the end of the time interval, I could use that as an estimate for this, the velocity of my particle over the whole time interval. And then I could say, yeah, sure, you could say 1 second times 1/2 of a meter per second, and that would give me 1/2 of a meter. So I can estimate that this object traveled 1/2 a meter in the first time interval. And in fact, I can do that over the whole time interval. So in other words, if I wanted to estimate how far did this object travel over the time interval from x equals 0 to x equals 4, I can actually add up the areas of the rectangle to get estimates for how far the particle traveled or the object traveled over the whole time interval for 0 to 4. So if we think about it that way, that time, x represents time, and f of x represents the velocity, then this calculation that we just made right here, we could say that this is an estimate of how far the object traveled from t equals 0 to t equal 4. So basically that process of estimating how far the object traveled, we can actually use the same exact process to estimate how far the object traveled if f represents the velocity, speed, and x represents the time. Before we move on, I just want to talk about the general case of estimating area under curves. So in this case, we're going to have n rectangles. This is the general case, so I'm not going to specify a number of rectangles. But let's suppose I want to estimate the area under the curve F from A to B, and I want to use rectangles to do that. The very first thing I'm going to do is I'm going to need to figure out, well, how long is the base of each rectangle? Okay, and the way that I'm going to do that is I'm just going to realize that the total distance here, the total length is b minus a, and I have n rectangles, so I'm just going to divide that by n, and we're going to call that delta x. So delta x is the length of the base of the rectangles. Now I also want to give a special name to the endpoints here that we see, because we use these to calculate the height. I'm going to call the first one x naught and the last one xn, and then of course the next endpoint is x1, and then we have x2, and it continues to xn. So the xi are just these are just going to be the endpoints. So now let's, using this notation, let's find an expression for Rn. So this is an estimate of the area when I'm using n rectangles and right endpoints. So let's start with the first rectangle. Here's the length of the base, and here's the height, f of x1. This is the first rectangle. So let's find an expression for the area of that rectangle. So again, here I have the base, here is the height, okay, so an expression for the area of that rectangle would be the height is f of x1, and the base is delta x. So multiplying these gives me the area. Next, I move on to the second rectangle. So I'm going to multiply the base times the height. The height is f of x2. So I have the base delta x times the height, which is f of x2. So it's given by my curve. So f of x2 is my height times my base, and then I can keep going in this manner. Finally, I get to the last rectangle. The base here is delta x. The height is f of xn, or f of b, if you want to say that way. And the area is given by f of xn times delta x. So this is a general expression for the estimated area where I'm adding up rectangles. I'm going to put this in a slightly more compact form using summation notation. So this is the sum from I equal 1 to I equal n of f of xi times delta x. Okay, so another thing you might be asking is, well, if I use more rectangles, can I get a better estimate? And the answer is yes. If you use more rectangles, you will get a better estimate. And actually, as long as the limit exists, if we take the limit as the number of rectangles goes to infinity, that will give us the actual area under the curve. So let me give you an expression for that, and we're just going to define it. The actual area under the curve, y equal f of x, from x equal a to x equal b, is given by the following limit. The limit is n, the number of rectangles approaches infinity, of our sum And then we just have the areas of the rectangles. This, and that's it. So this is the area when this limit exists. One other thing I want to point out is that when you actually go to calculate this area, you might be interested in, well, how do I calculate xi? Well, notice that x naught is just a, x1 is just a, plus I've added delta x. To get x2, I just add another copy of delta x. And to get x3, I just add yet another copy of delta x as we move along the x-axis. So xi is actually equal to whatever a is plus I times delta x. So this gives you an expression for xi, and we have an expression up here for delta x, and which allows you to always find an expression for this area.